Our final topic in this part of 0007 is eigenvalues and eigenvectors. This is something we're going to return to in the next section on linear algebra. Here's the definitions. Take an n by n matrix A. An eigenvalue of A is a number R such that there exists a non-zero vector V with AV is equal to R times V. Non-zero means not the zero vector. A vector with this property is called an R eigenvector of A, or sometimes an eigenvector with eigenvalue R. And finally, a vector which is an R eigenvector for some R is called just an eigenvector of A. Let's look at an example. We take A to be the matrix 1, 1, 1, 1. Then you can check that A 1, 1 is equal to 2 times 1, 1, and A 1 minus 1 is equal to 0 times 1 minus 1. That tells you that this vector is a 2 eigenvector of A, and this vector is a 0 eigenvector of A. Here's another way to write the eigenvector definition, which comes in handy sometimes. An R eigenvector of A is precisely a non-zero solution to the matrix equation A minus R times I times X equals 0. The reason for that is that if A minus Ri times V is equal to the 0 vector, and V is non-zero, well, just expanding this, you get AV minus RIV equals the 0 vector. And so, because I times V is just V again, we can rearrange this to get AV equals RV. So V is an eigenvector, in fact an R eigenvector. Conversely, if V is an R eigenvector, so AV is equal to R times V, and V is non-zero, then we can rearrange this. So if we look at A minus R times I and multiply this into V, well, then you will get AV minus RIV, so just RV. So you'll get the 0 vector. So V is a non-zero solution of that matrix equation. So how can we find eigenvalues for a given matrix? Well, there's a very easy criterion based on the observation we've just made. A number R is an eigenvalue of A if and only if the determinant of A minus Ri is 0. The proof now is straightforward. If the determinant of A minus Ri is 0, then A minus Ri is not invertible after our work in video 27. So, by the work at the end of video 24, there's a non-zero solution, V, to the matrix equation A minus Rix is equal to 0. That non-zero solution is precisely an R eigenvector for A, so R is an eigenvalue of A. Conversely, if R is an eigenvalue of A, that means there is an R eigenvector V. V is a non-zero vector such that AV is equal to R times V, so rearranging that like we did on the last slide, A minus R times the identity multiplied into V is 0. That's a non-zero solution to the matrix equation A minus Ri times X is 0, so A minus Ri is not invertible, again by the end of video 24. If it's not invertible, then again by video 27 its determinant is 0. So the key to eigenvalues is looking at this equation here. And so we make the following definition. The characteristic polynomial of a matrix A, which we write as chi A, and then a variable, sometimes x, is defined to be the determinant of A minus xi. So this variable here is a number, some kind of number, it represents a number. And what we've just seen is that the eigenvalues of A are precisely the roots of the characteristic polynomial. So let's follow the example that we did before. A will be the same matrix, 1, 1, 1, 1. We're going to work out its characteristic polynomial. Chi A of x is defined to be the determinant of A minus x times the identity, which in this case is the determinant of the matrix 1 minus x, 1, 1, 1 minus x. That is 1 minus x squared minus 1, which if you simplify is x times x minus 2. Now, since the eigenvalues of A are exactly the roots of chi A, the only eigenvalues of A are 0 and 2. So you might wonder now, okay, I know how to find the eigenvalues of a matrix A. How could I find the corresponding eigenvectors? In that example in the first slide, I just pulled the eigenvectors out of a hat. So how could we find them if we didn't know them? Well, this is simply a matter of solving linear equations. You already know how to do this, because as we observed before, an eigenvector with eigenvalue r is a non-zero solution to the matrix equation A minus Ri times x is equal to 0. So if you forgot what the 0 eigenvectors for A were, you would simply solve the matrix equation 1, 1, 1, 1, then whatever variables you like is equal to 0, 0. And the non-zero solutions to that equation will be precisely the 0 eigenvectors. Similarly, if you wanted the 2 eigenvectors, you'd have to solve 1, 1, 1, 1 minus 2 times the identity multiplied into an equation, a vector is 0, 0. In other words, you're solving minus 1, 1, 1, minus 1, x, y is equal to 0, and the non-zero solutions to this matrix equation are precisely the 2 eigenvectors. So in summary, first of all, an R eigenvector of a matrix A is a non-zero solution to the matrix equation A minus R times the identity multiplied into a vector x is the 0 vector. Another observation we could make is that if A is n by n, then chi A of x is a polynomial in x of degree n. That's because in the sum defining the determinant, we always have products of n terms. Now the eigenvalues of A are the roots of the characteristic polynomial, and this characteristic polynomial is a polynomial of degree n, so it has at most n different roots. And what that tells us is that there are at most n different eigenvalues for an n by n matrix A.